Hello, welcome to the second part for my talk on Morse quasiflats for the nearly carbon-neutral geometric topology conference. So here's the outline of the second part. So we'll start with some alternative characterization of Morse quasiflats, and then we will discuss some key properties of Morse quasiflats, such as invariance and quasi-symmetry and asymptotically conicality. And then we'll end the talk with by mentioning some first application. Let's start with some basic things on asymptotic cone. So I take a metric space, asymptotic cone. The metric space is basically that's trying to zoom out the metric space further and further and trying to take some kind of limit. The limit exists, but it's usually not unique and depends on various choices. For example, if I take X to be the Z2 with the standard word metric, we can think about this as a grid, the unit grid in R2. As we zoom out, further and further, then the grid becomes dense, more and more dense, and then the limit is going to be R2 with the L1 metric. Another example to have in mind is if X is the hyperbolic space, we know that every triangle in the hyperbolic space is delta thin. If we zoom out, then the triangles become thinner and thinner. So in the limit, all the triangles are zero thin. That means the limit has to be a tree. So asymptotic cone are actually very helpful to characterize certain properties of a metric space. So one example would be to characterize Gromov hyperbolicity. A metric space is Gromov hyperbolic if and only if each asymptotic cone of X is a metric tree. And the general principle to characterize a metric space through its asymptotic cone is the following. So suppose all the asymptotic cone of X satisfy some property, let's say property P, then one can usually deduce that the space itself also satisfies a related property P prime. P prime, usually P prime is not exactly P, but they are related, and P prime is usually a cross version of P. For example, let's go back and look at this Gromov hyperbolic example. So in this case, we know that all the asymptotic cone, the triangles in all the asymptotic cone are tripods, so they're zero thin. That's my property P. Then we know that X satisfies P prime. P prime, the property P prime is that all the triangle is delta thin for some delta. So you see that P prime is some kind of relaxation or some cross version of P. But in general, the relation between P prime and P might be a bit more subtle. And we need to handle this a bit more carefully. So now let's look at asymptotic cone characterization of Morse quasiflats. Let's start with the dimension 1 case. So the Morse quasi-geodesic. Let's first look at some special Morse quasi-geodesic. Let's first assume our ambient space is hyperbolic. Then in this case, any quasi-geodesic is Morse. And let's pass through the asymptotic cone and see what we see over there. So if we pass through the asymptotic cone, we keep zoom out, the hyperbolic space will become a tree and the quasi-geodesic will become a line. So now we want to start with a property which characterizes how a line could sit inside a tree. So which is the following property. We say a line in a space is rigid if for any segment in this line and any path in the space which connecting two endpoints of this segment, this path must cover this segment K. So as you can see that this is true if you have a line sitting inside a tree, but we sort of extract this property and formulate this property for any line in any kind of a space. Okay. Now let's look at asymptotic cone characterization of Morse quasi-geodesic, basically motivated by this. So we can, which is that a quasi-geodesic in the metric space is Morse if for any asymptotic cone the limit of this quasi-geodesic is rigid in the ambient asymptotic cone. So in this case, compared to the Gromov hyperbolic case, the asymptotic cone don't have to be a tree everywhere, but it has to behave like a tree along the limit of this quasi-geodesic. This is what this characterization really says. So now let's try to look at the higher dimensional generalization of this. So first, we need to define what does it mean for bidirectionally embedded flats to be rigid. So let's take a n-dimensional quasi-flats. And let's pass to the asymptotic cone. Let's zoom out and take a limit. As you zoom out and take a limit, the additive constant of the quasi-flats go to 0. So in the end, the limit is going to be an n-dimensional bi-Lipschitz embedded flats. And then we define what it means for this flats, bi-Lipschitz embedded flats, to be rigid. So now we just do it a little by little. So in the dimension 1 case, we have this segment K inside L. So now I'm going to replace by an embedded disk inside this bi-Lipschitz flat. And so now in the one-dimensional case, we consider a path connecting the two endpoints of the segment. In the high-dimensional case, we consider any chain whose boundary is the same as the boundary of the disk, but we want to write it in a homological language. We say the boundary of this chain alpha is basically equal to the homology class represented by the boundary of the disk and times k. K is going to be some non-zero integer. And then, so now in the one-dimensional case, we say this path cover K, and then in a high-dimensional case, we say this chain, the image of this chain covers D. So this is the definition of rigidity in high-dimensional case. And now we can basically imitate this definition of asymptotical capitalization of Morse quasiflats, and then we can give our second definition of Morse quasiflats. So we say a quasiflat is Morse if for any asymptotic cone, the limit of this quasiflat is rigid. So this is the second characterization. So now let me mention another characterization, which is called piece property. This property is actually very useful in certain situations, and it is even new in the one-dimensional case, even new for the Morse quasi-geodesic. Again, let's start with the one-dimensional situation. Let's take a rigid line inside some metric space. Imagine that we're in the asymptotic cone. And I take 2 point PQ in this rigid line and join them by this path beta. So beta is this purple path. We already know that since L is rigid, so the purple path has to cover PQ. The rigid actually tells us a little bit more about this. So let's say, suppose beta is first traveling along L, and then at some point it leaves L. I want to claim that the point it leaves L and the point it come back to L has to be the same point. If these 2 points are different, then I'm going to see a subsegment of L, which is not covered by the subsegment of beta where you leave and then come back. And this contradicts the rigidity of L. So we have this very curious property that whenever beta leaves L, then you have to come back to L at the same point. Then this gives us a decomposition of beta into beta 1 and beta 2. And the beta 1 is basically this union of these bubbles. And in general, there may be infinite many bubbles over there. And beta 2 is basically part, the second PQ inside L. So we have this piece decomposition. I want to say a bit more about what is special about piece decomposition. So if you take a line which is not rigid, you can still get some decomposition by just look at the part of the line which is part of beta which is outside line, and the part of the beta is inside line. You can always get a piece decomposition in general, but what is special about this piece decomposition? So there are 3 properties. The first property is this beta 1, the part which is outside L. Then you close it up in a natural way. It has to be a cycle. So there's no boundary. So these are cycles. And then second, beta 1 and beta 2, they have no dimensional overlap. So their overlap are on these points, which is 0 dimension. And then we'll know exactly what is beta 2. Beta 2 is basically the canonical filling between P and Q inside L. Now let's try to generalize this to high dimension. So we have to replace this rigid line by some bi-Lipschitz flat, which come from the cone of some quasi-flat. Now we have to replace this 2 point PQ by a codimension 1 cycle inside the bi-Lipschitz flat. And we consider beta. So in this case, beta is supposed to be an n-chain whose boundary is this alpha. And I want to say beta has a similar piece decomposition where beta 1 is basically a bunch of cycles, and beta 2 is the canonical filling of this alpha inside the bi-Lipschitz flat. And if for any alpha and any beta, we have such piece decomposition which satisfies these three conditions, then we say that this bidirectional flat f of omega is we say this flat has peace property. Now we can characterize Morse quasiflat in a third way. So we say a quasiflat in a metric space is Morse if for any limit of this quasiflat in any asymptotic cone, we get a bidirectional flat which has the peace property. So here I'm actually skip a lot of technical details. So let's go back to this decomposition to see what's the issues if we're trying to formulate this precisely. So let's take beta 1, this beta, and we want to define beta 1. Intuitively, beta 1 is supposed to be the part of beta which does not intersect L. And we take that part and we somehow take the closure, so we close it up and we get a cycle. But imagine that we're in a high dimensional situation and we work with singular chains or ellipsis chain. Then beta 1 is not clear what is the part of this chain which is outside L. And it's not clear what will you get if you take the closure. And it's not clear, not even clear how large is your closure. You may have a lot of noise because your chain may be wandering around in the space. And even if you can take a closure, it's not clear why the closure has a structure of a cycle. So these are the problems, which indicate that it's not so convenient if we're trying to use the singular chain or this chain to set up this decomposition. However, it's possible to set up this decomposition to use the theory of metric current, so which is another sort of homological theory in metric space, which has some metric theoretic flavor. So the advantage of that is you can always ignore the things of measure 0, and then that can be used to set up these things pretty cleanly. Now let's look at the equivalence of definition. So the first theorem I want to mention is that let's take x and y to be cat 0 space or combable group. So combable group contain a lot of examples. For example, all the cat 0 group, automatic group, or mapping class group, or semi-hyperbolic group, they're all combable group. And let Q be a n-dimensional quasi-flat. And then the following are equivalent. The first is that Q has super Euclidean divergence in the sense we already covered in part 1 of the talk. And the second is this rigid characterization. And the third is the characterization through the peace property. And then these three characterizations are equivalent. And also we know that the quasi-summation is going to map Morse quasi-flat to Morse quasi-flat. So here's some remarks. So we actually have more equivalent relation in our paper, so which is already an archive. So we have almost 10 equivalent relations, and the different characterization are useful in different situations. And we also have a generalization of the contracting properties for Morse quasi-geodesic to high dimensional cases. So recall that for Morse quasi-geodesic, the contracting property was formulated by looking at the nearest projection from 2 points inside this quasi-geodesic. So in high dimensional case, one might want to consider nearest point projection from the whole space to a Morse quasi-flats, but this turns out to be a huge mess. So that's why we didn't do it in that way. So instead, we're using some form of relative plateau problem to set up this contracting property. And the second remark is that here we require x and y to be cat 0 or combable, but in the article we actually work with much weaker assumptions. So the space only have to satisfy some very weak form of non-positive curvature, and then we have all this equivalence and QI invariance. Now let's look at the next topic. So we want to generalize Morse lemma to the context of Morse quasi-flats. But for simplicity, let's take x to be a cat 0 space. If we already know x is a Gromov hyperbolic, then okay, any quasi-geodesic is at finite Hausdorff distance from a geodesic. That's the Morse lemma. If x is not Gromov hyperbolic, then we still know Morse quasi-geodesic at finite Hausdorff distance from a geodesic. Now it's natural to ask, okay, let's take a Morse quasi-flat. Is it true that Morse quasi-flat are at finite Hausdorff distance from a flat? Unfortunately, the answer is no. Let's look at some example together, and then this example will tell us what should be the correct formulation for the Morse quasiflats, for the Morse lemma for Morse quasiflats. Let's take X to be a product of two hyperbolic planes, and let's try to look at examples of Morse quasiflat in this space. So first, notice that the T boundary of this space is basically a complete bipartite graph, more precisely. So let's look at the T boundary of X1. So each point is represented by a ray, geodesic ray in X1, and the T boundary of X1 has the discrete topology because X1 is hyperbolic. And the similar things holds true for T boundary of X2. Then the T boundary of X is basically the complete bipartite graph on this discrete set of points, T boundary of X1, and this discrete set of points which come from T boundary of X2. More precisely, each edge in the T boundary of X connects a point in the T boundary of X1 and another point sigma 2 in the T boundary of X2. So from a geometric viewpoint, sigma I corresponding to a ray, Ri sitting inside my factor xi. And the edge basically corresponding to the quarter plane, which is this R1 times X2 inside X. Now let's take a cycle inside the T boundary of X. Basically, it's a cycle in this complete bipartite graph. Then it's made of a sequence of edges. That means the cycle is going to correspond to a collection of quarter planes in X, assembled in a cyclic fashion. So adjacent quarter plane is going to intersect closely along one of their boundary component. And it turns out that the union of this quarter plane actually form a Morse quasiflat. And then it's clear that most of this Morse quasiflat cannot be close to flat. So the Morse quasiflat is also close to a flat if only if you have 4 quarter planes. But if you could have cycles with 6 quarter planes or 8 quarter planes, that they cannot be also close to a flat because the volume growth is not correct. So now this tells us, so we cannot expect that in general Morse quasiflat are close to flat. However, we see from this example that we still sort of see that the Morse quasiflat is sort of straight because it's made of these quarter planes, and each quarter plane is straight. So there's no bending or spiraling like what we discussed before. So now I want to sort of give a rigorous formulation of what we mean by a Morse quasiflat has to be straight. So again, so we take, for simplicity, work with K0 space, and I take a base point, and let's look at T boundary. And then the points in the T boundary are geodesic rays emanating from P, and the distance are basically given by the asymptotic angles between these rays. So now the way to say that the Morse quasiflat is straight is the following. So roughly speaking, the thing we want to prove is that the Morse quasiflat Q has a well-defined boundary. So it's some subset of the T boundary, such that if you compare this quasiflat Q to the cone over this T boundary, that means we just look at the union of all these rays starting from your base point P and go to a point in this subset, in this T boundary of Q. So this is basically a union of geodesic rays. And then we want to say that this quasiflat Q and this cone is sublinearly close. This would be a way of saying that Q is straight, as Q is close to a union of rays. Now let's look at the precise formulation. So let's take Q to be a n-dimensional Morse LA quasiflat. And then there is a subset of the T boundary of X, which we define to be the T boundary of Q with the following property. Now we look at the portion of Q inside a large bore of radius R. So R is some large number, and this BP of R means the bore centered at our base point P and of radius R. And also we compare to the portion of the cone which is inside this large bore of radius R. And I want to say that the Hausdorff distance is less equal than R times some sublinear factor. And this sublinear factor is going to approach 0 as R go to infinity. So this is the precise formulation of asymptotic conicality. And of course, we can have some control of this sublinear factor delta. It's depend on various parameters of the quasi-flat and depend on where is your base point. Another thing I want to mention is that this boundary of Q actually has more structure. It's not just a subset, it's actually a cycle. So just think about the H2 times H2 case. We already seen that this quasi-flats that corresponding to cycles in this bipartite graph in general. So the T's boundary of X is a very complicated topological space, but still this Q has some nice structure as a cycle. Now let's look at some more result in this direction. So we also have the uniqueness result. Suppose we have two Morse quasi-flats such that they have the same boundary cycle at infinity, then they're more or less the same in the sense that the Hausdorff distance is finite. And this C, the estimate of Hausdorff distance, also only depend on the Morse property of this quasi-flat. Another thing is we have the following rigidity result. So again, we look at the Morse quasi-flat, and we're asking when we know that the Morse quasi-flat is actually close to a flat. We know this is not generally the case. However, as long as the volume growth of the Morse quasi-flat is at most Euclidean, then we can conclude that the Morse quasi-flat is actually Hausdorff close to a flat. Again, the Hausdorff distance can be controlled on the Morse data of the Morse quasi-flat. So again, so the example you have in mind is this Morse quasi-flat in H2 times H2. So if you only have 4 quarter planes, then the volume growth is Euclidean. So we know that close to flats, if you have 6 or 8 quarter planes, then the volume growth is bigger than Euclidean. So they are not close to a flat. Now let's talk about some first applications. So this two theorem is going to be the immediate consequences of what we already have before, and this gives rise to some nice structural result on Cat0 cube complex. So we take X to be a finite dimensional proper Cat0 cube complex. Then we can conclude that every k-dimensional Morse quasi-flats is basically Hausdorff close to a collection of Cat0 orthed. So the example you have in mind is still this H2 times H2 example. In that example, all the Morse quasi-flats, which are actually two-dimensional quasi-flats, they are actually Hausdorff close to a union of quarter planes. And a similar structural theorem holds for Cat0 cube complex. Somehow the cubical structure confines the structure of the Morse quasi-flats. So every quasi-flat has to be close to a union of orthen, which are kind of high dimensional analog of quarter planes. Now we have the last application I want to mention. Again, it's an immediate consequence of what we discussed before. It's another version of Morse lemma for Cat0 cube complex. So the motivation comes from the example I mentioned at the beginning of the part 1 of my talk. So we already know this nice fact that if you have two hyperbolic space and you have a quasi-symmetry, then the quasi-symmetry is going to send geodesics to geodesics. Now we can ask, okay, suppose let's take two spaces which are not necessarily hyperbolic. Then is it possible to prove some theorem that says that the quasi-symmetry is going to send a flat to a flat after find a Hausdorff distance? And this is what we want to do in this theorem in some class of cube complex. So we take the universal cover of compact special cube complex. So this is our Cat0 space. And if we have a quasi-symmetry between them, then we know that the quasi-symmetry is going to send a Morse flat to a Morse flat up to find a Hausdorff distance. Notice here we are saying about Morse flat, not Morse quasi-flat, because Morse flat in this special case of special cube complex, they can describe combinatorically. So now this gives you the link of or give you some hint of how the quasi-symmetry would preserve the combinatorics of special cube complex, because we already know the set Morse flats to Morse flats, and the Morse flats can be described in combinatoric terms concretely for this special cube complex. And this basically link this will be serve as a link between the combinatorics of these two special cube complex, and this will be a very handy quasi-symmetric environment if one want to study QI classification of special cube complex. And actually, similar theorems play an instrumental role in the literature where people are studying quasi-symmetric classification of right-angle Artin group. Okay, so we also expect that phenomena like these two theorems also holds more generally for more general class of Cat0 complexes like the Davis complex for Coxeter group, and we expect to have more applications. Thank you for your attention.